Hi, welcome after the coffee break. So the first speaker of the second session of our little Central European part of this conference is Federico Berlai from the University of Vienna, and he'll be talking about automorphism groups of Cayley graphs of Coxeter groups.
Yes, so thank you, Michal. Yes, so really, I would like to thank you and the organizers for giving me the opportunity to speak here in such wonderful global event. And yes, so I will talk about some recent joint work that Michal and I have been doing on automorphism groups. So I'll start with a little bit of context. Okay. So whenever we have a graph delta, later on this delta will always be a Cayley graph for some finitely generated group. We can consider the group of automorphisms of this structure. So the maps that are bijections on the vertex set and that preserve adjacency. So in this group has well, a topology, which is called the permutation topology or the pointwise convergence topology. And a base for the identity for this topology is given by these subgroups UF, where F is any finite set of vertices. So this UF is the finite intersection of vertex stabilizers, where the vertex X is an element of my finite set F. And yeah, so this topology has some properties. For instance, it is totally disconnected. And whenever the vertex set of delta is not too big, the topology is second countable. So this base will be countable. And it is actually locally compact if the graph is locally finite and connected. So in particular, if our graph delta, as it will be in this talk, is a Cayley graph of a finitely generated group with respect to a finite generating set, all these conditions are met. So we have a nice tdlc, totally disconnected, locally compact, second countable group G. And now the natural question is to understand this topology. I mean, the natural problem is to understand the topology. And the question I will address in this talk is understanding when this topology for specific families of graphs delta is not discrete. And yeah, so we did so for Cayley graphs of Coxeter groups. So yes, I'll start with recalling what a right-angle Coxeter group is. It's defined in terms of a simplicial graph gamma, which is also finite because we want the group to be finitely generated. And well, the group will be generated by the vertices of this graph. All generators have order 2, and some generators commute between them. X and Y commute if and only if we see an edge in this finite graph that connects the vertex X and the vertex Y. For instance, if we have this finite graph, delta, then, well, the corresponding right-angle Coxeter group is generated by 4 involutions of order 2, and they cyclically commute, modulo 4. Xi and Xi plus 1 commute. And because the generators have order 2, notice that we can replace, well, this relation, the commutator of X and Y equal to the identity, with the element xy to the power 2 equal to the identity. Okay, and to generalize this to more general Coxeter groups, we will replace this xy to the power 2 equal to the identity with more general, with higher powers. So we start with again with a simplicial graph, and we put weights on the various edges. And well, so we will get a group with this presentation, which is maybe confusing, but let's see some examples. Here we have a graph with a weight, an edge with weight 3 and 2 edges with weight 2. If there is no number, then as in the right angle Coxeter case, the weight is 2. And maybe here we have another graph, which is different, not isomorphic as graphs, with just one edge and weight 6. And actually, the two presentations are given here define the same group, which will be a dihedral group of order 12. Okay, other examples. As we saw, this is the graph of before with colored labels. And the Cayley graph is, well, it's a finite graph because the group is finite. On the other hand, if we have this graph, so the weight here is 2, it's hidden, the group is infinite, and the Cayley graph with respect to this generating set given by the graph is well, this branched structure. Okay, now the question that was given before translates into this. So we are fixing a finite simplicial graph gamma with weights on the edges. We consider the Cayley graph of the Coxeter group defined by that with respect to the generating set given by the vertices. And we want to understand when the topology on the automorphism group of this Cayley graph is discrete and when it is not. And this is what I will answer in the following, in this talk. And let me, really stress that we are not allowed ever to change the generating set. So this is not a question about the Coxeter group we are considering. It's about the Cayley graph. And if we change the generating set, we change the Cayley graph, and the answer changes. So there are recent wonderful results by Lehmann and de la Salle that prove that for almost all groups, if you are allowed to change and take bigger and bigger finite generating sets, then actually this automorphism group will always be discrete or as small as possible. And the results in this talk are on a perpendicular direction. We don't change the generating set, and we are interested in understanding when the group is actually not discrete, so big, uncountable. Great. And well, the result that well, or the starting result that interested us was this. Well, it's the answer to this question for the case of right angle arting groups. So a right angle arting group is the same thing as a right angle Coxeter group, but the generators now have infinite order. They are not elements of order 2. And it turns out that the topology, the pointwise convergence topology on this automorphism group is countable. So it's discrete if and only if the graph is complete. As soon as there is an edge missing in this finite graph delta gamma, then the topology is uncountable. The topology is not discrete. The group is uncountable. So from this, we jump to right angle Coxeter groups and then to more general Coxeter groups. And yeah, maybe the first thing that one can think of when dealing with these kind of questions is, well, thinking of the subgroup constructed by automorphism, which are label preserving. So the Cayley graph, for instance, in this case, well, any Cayley graph is a label graph. And so one subgroup inside here is the one of the automorphism that preserve labels. So let's call these label preserving automorphism translations. So these are not graphical translations because this reflection along the dashed vertical line actually is label preserving, but it's a reflection. It doesn't move things. I mean, it's not a translation in the graphical sense. They are called like this because they will correspond to multiplications on the left. So if the Cayley graph is a right Cayley graph, these will be label preserving. Automorphism will be multiplication on the left on the set of vertices, which correspond to the elements of the group. So yes, so this is a very nice subgroup to look at. And actually from this picture, we can see another thing that we will explore more in the following slide. So let's consider the vertex V, and well, let's call well, this reflection or this translation alpha. So V is mapped by alpha to the identity. What we can see is that if we consider the edges incident at V, for instance, and the edges incident at alpha of V, which in this case is the identity, well, because alpha is an automorphism of this graph, it will induce a bijection between these set of edges. So the edges incident at V and the edges incident at alpha of V. And so it induces a bijection between the labels of these edges. And actually, it turns out that this is not just a bijection between the labels. It's an automorphism. It's a symmetry of the finite simplicial graph, because labels of the Cayley graphs are vertices in the finite simplicial graph. So we have this situation. Yes, given any automorphism alpha and any vertex V in the Cayley graph of the Coxeter group, this pair uniquely defines a symmetry of the finite simplicial graph gamma. And here, well, if the graph gamma has no weights, then this is it's a symmetry of the finite simplicial graph, as we all know. If the graph has weights, then by the symmetries of this weighted graph, I just mean bijections between the finite vertex set that preserve the weight, the weight function. So if it's unweighted, all edges have weight 2, and yeah, this this generalizes the notion of automorphism for an unweighted graph. Great. For instance, another example, if we take this vertex V and we consider the automorphism that reflects along this dashed axis, well, this time, well, the label blue is fixed, but the label red and olive are switched. So sigma alpha V is the following non-trivial symmetry that interchanges the two vertices here. And yeah, probably the first result we can think of is that there is a relation between let's call these sigmas the local action of alpha at the various vertices. So there is a relation between the local actions that we can see in the Cayley graph and the automorphism alpha. And in particular, if this group of symmetries of the finite simplicial graph is trivial, then all elements of the automorphism group of the Cayley graph must be label preserving. Yes, but wait, label preserving where generating a group which is isomorphic to the Coxeter group. So in particular, this group of automorphism is finitely generated, and thus it is countable, and thus the topology must be discrete. Okay, let's prove this by picture. Or okay, here are some examples of graphs with trivial automorphism group, symmetric group. and the proof is by picture. So take an automorphism, alpha of G, and look, well, and take one vertex in this Cayley graph. We want to prove that alpha is label preserving. Well, let's consider the ball of radius 1 around V and alpha of V. Yeah, but now sigma alpha V must be the identity, because this is the only option. The automorphism is trivial. The automorphism of the finite simplicial graph is trivial. So after all, alpha on the ball of radius 1 must preserve labels, because this is the only option. But again, if we repeat this process, because the Cayley graph is connected, we will cover the whole Cayley graph. And so it is true that alpha is label preserving on the whole Cayley graph. So it is a translation. And so the whole group G, the topological group G, is countable and discrete. Okay, this is the first result we can think of, but actually this strategy of proof is more general. So if we consider this property, so consider a simplicial graph with weights maybe, and suppose that for all vertices in the Cayley graph, for all vertices in this graph and all automorphisms of this finite simplicial graph, if one automorphism restricted to the star of X is trivial, then this implies that sigma, this automorphism, is already, is trivial on the whole graph. This is quite restrictive. For instance, if the automorphism group of gamma is trivial, then this is trivially true, because sigma can only be the trivial symmetry. But this is true also for these graphs, for instance, that have non-trivial symmetries. This property is true is met for these graphs. Okay, it turns out that this property, which is a geometric property on the simplicial graph defining the Coxeter group, this is equivalent to a statement about topological groups. So for a weighted graph gamma, then this condition is met, is true if and only if the topological group, the group of automorphism of the Cayley graph of the Coxeter group, is discrete. So this is nice because we can see we can say something about a topological group G being discrete or not in geometric terms with respect to a finite simplicial graph. And actually, if it is discrete, being discrete is equivalent to being countable for such groups, because they are second countable. But in particular, they are not just countable, they will be finitely generated. And yes, all automorphisms are almost translations, meaning that this local action defined before is constant. Maybe it's not the identity element. It's not the identity it's not the identity, but it's constant. Yeah. So this is the condition of before. This is the theorem, and yeah, let's talk a little bit about the proof of these things. This is the key fact, and again, this key lemma, say, or key result underlines that there is a strong relation between the local actions, so these sigma symmetries induced by the automorphism alpha, and the structure of alpha itself. So let's try to untangle this statement. So here we have an automorphism alpha of our Cayley graph, a vertex V in the Cayley graph, and another vertex Vx in the Cayley graph, and V and Vx are joined by an edge, because X is a generator of the group. And what this statement says is that the permutation induced around V by alpha and the permutation induced around Vx by alpha, maybe in general they do not agree, they are not the same, but they must agree on the star of X. So, or on the other vertices in the finite simplicial graph that are connected by an edge to X. But wait, let's try to use this with the star condition. Now, if we compose, say, sigma alpha v with the inverse of sigma alpha vx, well, we see that this composition on the star is trivial just by this equality. And then this condition implies that actually the composition is trivial on the whole graph gamma. So the local action of alpha at v and the local action of alpha at any neighbor of v is the same, because of this, of the star condition. But actually v and the generator x were arbitrary elements, and because again the Cayley graph is connected, this just means that this local action must be constant on the whole Cayley graph. And well, then you need to prove that the subgroup generated by automorphisms which have constant local action actually is finitely generated. It's that it's the Coxeter group semi-direct product with well, the automorphism, the finite automorphism group of this finite graph. Great. And for the other implication, well, you need to construct by hand an uncountable family. And well, let me hint at the construction for this finite nice graph. So we saw the Cayley graph of this before, of the right angle Coxeter group before, and it's like this. It has some branching structure. And what's the idea? Well, take one vertex and take an infinite ray going down at infinity. So this ray that does not backtrack, well, will pass through infinitely many such little squares, commuting squares. And well, as you can maybe understand from the picture, you can, at each square, you can either decide to flip well, flip the square or not, and yes, because the squares are infinitely many, you have uncountable many choices you can make. And well, one proves that each so these automorphisms are pairwise different. And so you constructed we constructed an uncountable subgroup in this automorphism group of this particular Cayley graph. And what's the point here? The point is that for this graph gamma, the star condition of before is not true. Why not? Because there is a vertex, which is this blue vertex. And well, if you look at, so this graph gamma has two automorphisms. The automorphism group of gamma is a cyclic group of order 2. One is the identity automorphism, and the other one is flipping these two vertices. And we can see that both automorphisms, when restricted to the star of this blue vertex, are the identity, because actually the star is just the vertex, and both automorphisms fix the vertex. Sorry. Both automorphisms fix the vertex, but the identity is certainly not equal to the other element here, flipping the two things. So the star condition is not true here. And yeah, so in this case, we could write down or draw the Cayley graph. For other graphs, you cannot draw the Cayley graph, or maybe the Cayley graph will even be one-ended, but still, whenever this star condition of before is not met, you can play this trick and flipping in uncountably many different ways parts of the Cayley graph. And so, yeah, this is the result again with the star condition embedded in the statement. And yeah, so thank you very much.
Okay, thank you, Federico. Do we have any questions regarding the talk?
Yeah, do you know if you get like a simple subgroup of G, similar to what happens for like groups acting on trees?
Yeah, with I don't know. We should think about this. But I don't know. That it's a natural question. Maybe restricting the local actions that one can see, but like for Burger-Moses group. Mm-hmm. But I didn't, or I didn't think about this yet in deep. So I don't have any answer.
Well, since I'm author on this, I guess I can answer partially as well. Like, yeah, as of now, we don't know, but as Federico said, like we're planning on having looking at some Burger-Moses type constructions if we can find some big simple subgroups, and perhaps to see if we can construct them by defining graphs that have simple group of automorphisms, but then I'm not entirely sure if this does not go against having separating sets in the graph. So yeah, that's the answer, I guess.
Yeah, it would be particularly interesting to see like one-ended simple groups coming out of this, so that they're definitely sort of different from the tree examples.
Mm-hmm. Mm.
Okay, any other questions? Well, if not, let's thank Federico one more time.
Thank you.
I'm still clapping on my own result. All right, and the next talk is in 2 minutes.